Good day to everyone. I am Deepak Kumar. I am a research scholar at Department of Computer Science and Engineering at IIT Roorkee, India. I will be presenting the following paper on behavior analytics, which is towards the engagement prediction, a cross-modality dual pipeline approach using visual and audio features. This is the outline of our work. I will be presenting uh, the introduction, methods that have been implemented, along with the detailed explanative results. So, in today's rapidly evolving world of artificial intelligence and machine learning, human-computer interaction has seen significant advancements. A crucial aspect of this interaction is engagement, defined as the degree of attention and involvement individuals shows in a task or interaction. Engagement play a vital role in effective communication and collaboration, both in human-human and human-computer interactions. Accurate estimation of engagement is essential to enhance user experiences in areas such as virtual meetings, education, and customer services. However, due to the dynamic and context-dependent nature of human behavior, engagement estimation remains a complex task. By integrating multiple modalities like facial expressions, speech patterns, and body language advances, AI techniques are now providing a more comprehensive understanding of engagement, improving the accuracy and adaptability of intelligent systems in real-time interactions. There are many challenges when we come to the engagement prediction, in which human behavior is complex and constantly changing, influenced by a mix of spoken words, body language, and the situation. Traditional methods often miss these details as they depend on basic measures or direct user feedback, which cannot fully capture how people engage. To better understand engagement, more advanced methods are needed that can took a different type of data together. Multimodal approaches, which combines facial expressions, body movement, and speech, provide a more complete view of engagement and help systems respond more effectively to human interactions. Our paper introduces a new cross-modality fusion method to tackle the challenges of engagement estimation using multimodal data. So the problem statement is like this. We have given a set of visual features and audio features. The aim is to develop a predictive network that estimates engagement level for each frame in a sequence. The goal is to ensure that the predicted engagement levels closely match the true engagement levels which are associated with each frames using the concordance correlation coefficient, that is called as CCC, as the evaluation metric. So we have the primary contributions of this paper is the accurate prediction and understanding of engagement levels in dyadic interactions. We present a novel sequence-to-sequence cross-modality hybrid fusion approach specifically designed to enhance engagement prediction by effectively integrating multiple data streams. Additionally, we perform an extensive evaluation study to evaluate the performance of our proposed architecture under different configurations, showcasing its robustness and effectiveness compared to existing methods in the field. We have used three data sets in our study, that is NOXI, which is multimedia 23 version, NOXI, which is additional languages, and the MPII group interaction dataset, which is also called as MPIIG. So in NOXI dataset, it has 64 sessions in English, French, and German, includes video, audio, and social behavior annotations. It serves as a benchmark for comparing in-domain model performances across multimediate 23 and multimediate 24 submissions. NOXI additional language. This extension feature sessions in Arabic, Italian, Indonesian, and Spanish, testing the model's ability to generalize across different linguistic and cultural contexts. simulating real-world applications. MPII Group Interaction Dataset. This dataset includes 22 sessions involving 3 to 4 participants plus an unpublished test set of 6 discussions. It provides detailed annotations on group dynamics, including eye contact and speaker turns, with added engagement annotations for out of domain evolution and domain adaptation. These datasets offer diverse and challenging scenarios to rigorously test our model's accuracy and generalization capabilities. We have used 4 types of features in our study, that is facial motion, and acoustic descriptors, clip visual features, and semantic embeddings. In the facial motion features, we utilize open face data, which provides 68 facial landmarks extracted from each video frame. These landmarks represent key points on the face. To quantify facial motions, we calculated the Euclidean distance between corresponding landmarks in the reference frame, that is first frame, and subsequent frames. We can see with this equation 1 is showing the calculation of the Euclidean distance. This distance captures the displacement of facial landmark over time, indicating changes in facial expressions, which are linked to engagement. The greater the distance, the more the landmarks has moved, indicating changes in facial expressions over time. These distances are compiled into a feature list to represent temporal facial motions. The temporal encoding of facial features is expressed with equation 2, where f is the total number of frames and n is the number of landmarks. This encoding helps in analyzing how facial expressions change over time, providing crucial insights into the engagement level of participants. Along with facial motion features, we have also used several more feature sets, like for the audio data. We have used provided acoustic features extracted using the OpenSmile toolkit, which provides a range of descriptors, including spectral properties that capture energy distribution across frequencies, mel frequency septal coefficients for perceptual sound characteristics, and pitch information. These features help in identifying important audio patterns such as tone, rhythm, and intensity, which are crucial for understanding the level of engagement. Additionally, we leverage the provided clip visual features for each video frame. Clip is designed to learn a joint embedding space for both images and text, capturing key semantic information such as attention, focus, and emotional expressions, which contribute to a richer understanding of visual engagement cues. To further enhance the model's ability to interpret the audio, we also utilize semantic embeddings generated by Facebook's Wave to Back 2.0 model. This model pre-trained on a vast dataset of 4.5 million hours of audio in over 143 languages, which provides deep insights into the semantic meaning of the spoken content, which it offering valuable information for comprehending engagement through speech. This is the overall architecture diagram of our proposed approach. As we can see in the diagram, the input video is divided into overlapping segments. We split the entire video into two second of sequence with a 1 second overlap, and we did the same for the audio. For each segment, we used 4 types of features in our study, that is facial motion, sound details, clip visual features, and meaning representation. We employed positional encoding and transformer encoders to capture temporal dependencies on each modality features. The extracted features from the facial motion and acoustic inputs are concatenated in the upper branch, while the features from the clip and semantic embeddings are concatenated in the lower branch, as we can see in the diagram. This strategy leverages the complementary nature of different modalities, providing a richer and more diverse features set of engagement estimation. This strategy was chosen for its ability to handle heterogeneous data efficiently, By first processing and concatenating related features within each branch, we can capture the intramodality dependencies effectively before combining them for intermodality interactions. This hierarchical approach helps in reducing the dimensionality and complexity of the feature space, making the subsequent fusion and integration steps more manageable and effective. After that, we have cross-modal fusion block. In our approach, we chose this fusion strategy because it effectively model complex interactions between different modalities, and we have used SELU activation in place of ReLU due to its self-normalizing properties, which help keep activations well scaled, facilitating faster convergence and improved training stability. By applying dance transformations and shallow activations, our model can capture non-linear relationships which are essential for understanding engagement signals. This fusion method enhances the robustness of our model and has been shown to outperform simpler concatenation techniques by capturing synergistic effects across modalities. Final block is MLP block or final prediction layer. The concatenated and integrated features are passed through a series of fully connected layers to obtain the final engagement predictions. The final output layer uses a linear activation to predict the engagement score for each time window. As we can see in the table, this table is a comparison of the overall CC scores on validation and test sets for various state-of-the-art methods. Our proposed method demonstrates superior performance compared to the baseline approach. Specifically, our cross-modality dual pipeline model achieves a global CCC score that is 0.23 points higher than the baseline. Additionally, we compare our results on the NOXI-based dataset. Those are previous studies. Overall, our proposed method achieves an overall accuracy of overall CCC of 0.792 on the validation set and global CCC of 0.64 on the test set. These results underscores the effectiveness of our approach. In this table, the highest CCC score is 0.79, which is achieved with facial motion fillers with open smile in the first pipeline and clip with BERT in the second pipeline. Our dual pipeline model uses a transformer encoder for self attention and multi-head attention, followed by cross-modality fusion to capture the specific pattern. Facial motion with open smile combination captures emotional specific facial and vocal features, while clip with BERT captures body patterns and spoken word context. MPIIG group interaction dataset CCC performance is lower due to feature distribution mismatch with NOXI dataset because incorporating MPIIG validation data during training improves performance. In this table, we presented results for different modality combinations, which is a unimodal, bimodal, and trimodal. In our approach, a model shows that audio features are more informative for engagement scores than visual features. Combining audio with visual features improves performance by leveraging complementary information, whereas the best results are obtained with the facial motion and BERT. One key observation is that visual features are more predictive of an expert compared to the novice. This could be due to the expert can shows the greater topic knowledge and enthusiasm, which exhibit more expressive facial and body movements. These are effectively captured by our features, whereas novice expressions may vary more based on their subject knowledge and interactions with experts. This table shows the evaluation study which we have taken with like a series with different sequence length and overlapping segments. So the results for different sequence length, the best performance is achieved with this 3 second with 1 second overlap, capturing the temporal details with minimum overlapping. Increasing the sequence length does not improve performance, likely due to diminishing returns or overfitting or feature redundancy. So, in the conclusion, in this work, we propose a novel method for engagement estimation by integrating visual and audio features using a deep neural network with transformer encoders and cross-modal fusion. Our approach effectively captures temporal dependencies and interactions between modalities, enhancing the accuracy of engagement prediction. By leveraging transformer encoders with positional embeddings, we preserve the temporal context of input features, which is key for understanding dynamic engagement patterns. Our cross-modal fusion mechanism combines with cellular activations ensures robust and accurate predictions. These are the key references that we have used to prepare the slides. Thank you for listening.